Okay. So first property which we are going to discuss today is called the change of scale property. Okay, if the Laplace transform of capital F is small f, then the Laplace transform of capital F of at, here the argument t has been multiplied by a constant a. Okay, the argument t has been multiplied by a constant a, so the Laplace transform of f of at will be 1 by a small f of s by a. Okay, 1 by a small f of s by a. And how do we prove that? We can prove it very simply. So Laplace transform of f of at is by definition integration from 0 to infinity e to the power minus st f of at times dt. Now let us substitute at equal to some other variable u. Okay, here a is a constant. So if I take the differential of this, I get a times dt is equal to du. So in this integral, in the first integral, if we replace at by u, what do we get? We get f of at becomes f of u, dt becomes du by a, here t also becomes u by a. So we get this expression, and here we have assumed that a is a positive constant. So when t is 0, u is 0. When t goes to infinity, here u also goes to infinity. Okay, that is fine. So we have this expression, and since a is a constant, this a can be taken outside the integral sign. So I have 1 by a here. So 1 by a e to the power minus s by a times u fu du, integral from 0 to infinity. And this is nothing but the Laplace transform f of s by a. Here we have the coefficient of u is s by a. So we have 1 by a small f of s by a. This is what we have obtained here. Okay. So the proof is very simple. Let us take an application of this as an example. If the Laplace transform of capital F of t is given by this expression, s square minus s plus 1 divided by twice s square, twice s plus 1 whole square divided s minus 1. If this is the Laplace transform of f of t, then find the Laplace transform of f of twice t. So we simply use this formula. Here a is equal to 2. So in this formula, we replace a by 2. So f of twice Laplace transform of f of twice t is 1 by a, that is 1 by 2, f of s by a. So you write 1 by 2 here, and wherever you come across the symbol s, wherever you come across the variable s, you replace it by s by 2. So this becomes s by 2 square, this becomes minus s by 2, this becomes s, and this becomes s by 2. Okay, we simplify this and get this final expression. Very simple. Okay, now let us look at the next property, and that is multiplication by t to the power n. Okay, so if the Laplace transform of capital F is small f, then Laplace transform of t times capital F. T times capital F would be minus the derivative of f of s. In general, the Laplace transform of t to the power n times f capital F would be minus 1 to the power n, the nth order derivative of f of s. Okay, the nth order derivative of f of s. Okay, first let us look at the proof for n equal to 1. So when n equal to 1, this becomes t f of t. So given f of s, this is the Laplace transform of capital F. This is the definition. Now let us differentiate both sides with respect to s. So if I differentiate both sides with respect to s, I get df by ds And when I take the differentiation inside the integral sign, it becomes partial derivative with respect to s. So if I partially differentiate this expression with respect to x, here we see that there is only one term which contains s, that is e to the power minus st. So if I differentiate this with respect to s, I get e to the power minus st multiplied by minus t. So I get e to the power minus st multiplied by minus t. The remaining terms remain unchanged. They do not depend upon s. So this minus, I bring it outside. What remains is e to the power minus st, t times f of t. And this is nothing but the Laplace transform of t of f of t. Okay, so this is nothing but the Laplace transform of t times f of t. So minus with the minus sign here. So we have df by ds is equal to minus Laplace transform of t of f of t. And repeated differentiation with respect to with respect to s will give us the higher order derivative, which is given here. When we differentiate f of s with respect to s n times, then we get this minus t to the power n, e to the power minus st ft dt. Because this is the only term which depends upon s, and when I differentiate it once, I get a factor of minus t. If I differentiate it twice, I get a factor of minus t whole square. If I differentiate it thrice, I get this coefficient minus t whole to the power cube. Okay, and so on. So if I differentiate this n times, I get this factor minus t whole to the power n. Okay, so this is nothing but the Laplace transform of minus t to the power n f of t. And this minus t, it can be written as t to the t times minus 1. So this can be written as minus 1 to the power n multiplied by t to the power n. And minus 1 is a constant, so I can take it outside. So this is the proof for general any value of n. For the general case where n can take any value. So let us look at one application. So we have Laplace transform of t square cos of at. And we know the Laplace transform of cos of at is s divided by s squared plus a squared. Okay, and from the property which we just saw, this multiplication by tn, Laplace transform of tn f of t, which is minus 1 to the power n, and order derivative of f of s. So here we have t squared. So this becomes minus 1 whole squared, second order derivative of the Laplace transform of cos at. And the Laplace transform of cos at is s by s squared plus a squared. And when we perform this differentiation twice, we get the final answer twice s times a square minus 3a square divided by a square plus a square whole cube. This is left as an exercise to you. You have to prove that this is equal to this. I leave this as your exercise. So we have seen how the Laplace transform changes when we multiply the function by t. Now let us look at how the Laplace transform changes when we divide the function by t. Okay, so division by t. For this, we assume that f of t is capital F of t is piecewise continuous on the interval 0 to infinity. 0 is included, infinity is not included, and it is of exponential order alpha, such that limit the right hand limit, that is the right hand limit when t tends to 0, f of t by t, if this limit exists, if this particular limit exists, and the Laplace transform of f of t is small f of s, then the Laplace transform of f, capital F divided by t is equal to integration of the Laplace transform small f with respect to some other variable from the limit, from the lower limit small s to infinity. Okay, where s is greater than the order exponential order alpha. Okay, so how do we prove this? Proof is simple. You take gt equal to f of t by t. Therefore, f of t becomes t times gt. And we already know the Laplace transform of this particular function. So Laplace transform of f of t is Laplace transform of t times gt, and this is minus the derivative of the Laplace transform of gt. Okay, so we have this expression. So if we integrate, this is the right hand side, this is the left hand side. So if we integrate both with respect to with respect to s from the limit s to infinity, what do we get? So if I integrate this, it becomes here minus, we have one minus sign here, so minus sign is retained here. So the integral of this becomes Laplace transform of g of t in the limit s to infinity. Okay, and that is equal to the integral of small f of s from s to infinity. And since s, the variable s, is used as a lower limit here, so we normally change the variable of integration to some other alphabet. So we have written it as u. So f of u du, because s, the letter s is already used here in the lower limit. Okay, so this can be replaced by u, this can be replaced by any other variable, omega, v, any variable you like, because the final answer will only depend upon s. The final answer of this integral will depend only upon s. It will not depend upon the integration variable. This is a definite integration. Okay, definite integral. So the final answer will depend only upon the limits. It will not depend upon the integration variable. Since g is piecewise continuous and is of exponential order, limit s tends to s tends to infinity, the Laplace transform of g is equal to 0. Okay, this we did as theorem number 2 earlier. If we have a function which is piecewise continuous and of exponential order, then in the limit s tends to infinity, Laplace transform of that function would be 0. This we did earlier, okay, as theorem 2. So since in the limit s tends to infinity, this term is 0. So what remains is only the value of this term in the limit s. Okay, so we get Laplace transform of g is equal to integration fu du from s to infinity. Okay, and hence the property is proved. Okay, so what is the property? Laplace transform of f of t by t is equal to integration of f from s to infinity, and we have proved it here. So let us look at an application of this property. Okay, find the Laplace transform of sine at by t. I repeat, find the Laplace transform of sine at by t. So division by t. So for the time being, we neglect this t in the denominator, and first we calculate the Laplace transform of sine at, and the Laplace transform of sine at is a divided by s square plus a square. Okay, so this is the Laplace transform of sine at. Here the t in the denominator means we should take the integral of the Laplace transform, okay, from the last property which we discussed. So Laplace transform of sine at by t, that is nothing but integral of Laplace transform of sine at, that is a by s square plus s square. So a by s square plus a square with respect to s from s to infinity. Here this s we can replace by some other variable u. Okay, so a by s square plus a square, the integral of this is nothing but tan inverse s by a. Tan inverse s by a, the limit s to infinity. Tan inverse s by a, limit s to infinity. So first we put s equal to infinity. So what is tan inverse infinity? Tan inverse infinity is pi by 2. If we take the range from 0 to twice pi. So in the range 0 to twice pi, the value of tan inverse infinity is pi by 2. Okay, so this is the the value of tan inverse S by A in the principal branch if we take the branch as 0 to, if we take the principal branch as 0 to twice pi. And the other is when the other is tan inverse S by A. So we get pi by 2 minus tan inverse S by A. So this is simple application of the division property. Now let us look at another example which is slightly more complicated but not so difficult. So find the Laplace transform of integration of sine u by u du. Okay, so first we have to apply the property where we take the Laplace transform of integration of an integral. Okay, and we know that the Laplace transform of an integral, okay, let me write it down here. The Laplace transform of an integral. Okay, so the Laplace transform of an integral, the Laplace transform of integral from 0 to t, 0 to t, some function f of tau d tau. Okay, this Laplace transform, what is this equal to? This is equal to 1 by s Laplace transform of f of t. Okay, so Laplace transform of integral of this is equal to 1 by s Laplace transform of f of t. So we use that property here. Okay, so the Laplace transform of integral is 1 by s Laplace transform of f of t. And what is f of t here? F of t would be sine u by u, and if we replace u by t, we get Laplace transform of sine t by t. We get it here. Okay, then after this we see that this is some function divided by t, and we saw from the last property that Laplace transform of some function divided by t would be equal to integral. Okay, so this is 1 by s we keep it here, and this Laplace transform, it becomes integral, this integral from s to infinity f of Laplace transform of sine t ds. Okay, this part is nothing but small f of s. Okay, so let us look at the next step. So this 1 by s we keep it as it is, and what is the Laplace transform of sine t? The Laplace transform of sine t would be 1 divided by s square plus 1. I write it as 1 plus s square, like this. And integration with respect to s from 0 to infinity. 0 to infinity. So this, the integral of this is tan inverse s. Okay, so the integral of this is tan inverse s, and limit s from 0 to infinity. So what, and when we apply the limit, we apply the limit only here, not to the s which lie outside. Sige mapanda level s to the limit applied to Roy, we shall apply the limit only here, because this 1 by s is outside the integral sign. Okay, so the limit s tends to infinity will not be applied here. So this is equal to 1 by s, and tan inverse infinity, as we have seen in the principal branch, it is pi by 2, and minus tan inverse s. We get this. Okay, and pi by 2 minus tan inverse s, it can be written as cot inverse s. So the final answer is 1 by s cot inverse s. So we have applied two properties here. First is Laplace transform of integral, and second is Laplace transform of division by t. So we have used two properties here: Laplace transform of an integral, and then Laplace transform of division by t. Okay. Now let us look at another property. How to find the Laplace transform of a periodic function. Okay, so let the function capital F be periodic with period capital T, so that f of small t is equal to f of small t plus capital T. So this is how we express periodic function. Okay. So this is how we express periodic function with period t. Okay. Then the Laplace transform of this function f of t is given by 1 divided by 1 minus e to the power minus s capital T. This capital T is the period. Then integration of e to the power minus st f of t dt. Here, this integrand is the same as the integrand we use in Laplace transform. The only difference is in the limit. The limit goes from 0 to the period capital T. In Laplace transform, it goes from 0 to infinity. Here, you should note that the limit of integration is the period t. The upper limit is the period t, the lower limit is 0. Okay, so that's the only difference. So how do we prove this particular property? How do we prove this? Okay, so let us start with the definition of Laplace transform. Laplace transform of f of t is by definition equal to this expression. Okay, now this limit from 0 to infinity, I can divide this limit into two limits. One is from 0 to capital T and the other from capital T to infinity. So this limit from 0 to infinity, I can split it into two limits, one from 0 to infinity, one from 0 to t, the other from t to infinity. The integrand remains unchanged. Recall. Now in this second integral, we substitute this t. We substitute t by tau. And what is the relation between t and tau? Tau is equal to t minus capital T, where capital T is the period. So tau equal to small t minus capital T. Okay. Then d tau is equal to dt, and t is equal to tau plus t. So in the second integral, we replace t by tau plus t, dt by d tau. So this Laplace transform, this first term, it remains unchanged. The first term remains unchanged. In the second term, we replace t by tau. So ft becomes f of tau plus capital T, and small t becomes tau plus capital T. Here we should remember that capital T is a constant. And when small t is equal to capital T, so when small t is equal to capital T here, if we put small t equal to capital T here, tau becomes 0. So the lower limit is 0. And when small t is infinity, that is when small t is infinity, tau is also infinity. Okay, because from infinity, if you subtract any finite number like capital T, the answer is always infinity. Okay, so the limit capital T to infinity changes to 0 to infinity. And f of tau plus t, and dt becomes d tau. Dt becomes d tau. So now we have substituted t by another variable tau related by this expression, and so we get the integration in terms of tau. Now we know that f is a periodic function with period capital T. So f of tau plus t is simply equal to f of tau, because by definition, this is the expression for periodic function. F of t plus tau is equal to f of tau. This is how we define periodic function with period t. So this becomes simply f of tau. Okay, and this e to the power minus s tau plus t, it can be written as e to the power minus s tau multiplied by e to the power minus s capital T. And since capital T is a constant, I can take it outside the integral sign, because this integration is with respect to tau. So here s is a constant, t is a constant. So e to the power minus st I have taken outside here. The first term remains unchanged. So I have done nothing to the first term. I have simply made my simplifications in the second term. So e to the power minus st, I have taken it outside. And then what remains inside is e to the power minus s tau f of tau d tau. And what is this? This is nothing but the definition of the Laplace transform of the function f of t. Okay, so this part we replace by Laplace transform of f of t. Okay, so we have on the left hand side Laplace transform of f of t, and we have on the right hand side e to the power minus st Laplace transform of f of t. So we take this term towards the left, take this term towards the left, and take Laplace transform of f of t common. Okay, so we take this term towards the left and take Laplace transform of f of t common. Then it becomes 1 minus e to the power minus st Laplace transform of f. Okay, Laplace transform of f. When I take common, this would be 1. This plus would become minus. So 1 minus e to the power minus st. So 1 minus e to the power minus st. Laplace transform of f is this right hand side, the first term on the right hand side, which I have left untouched. So this is integration from 0 to t, e to the power minus st ft dt. Okay, so I divide both sides by this coefficient. So finally I get Laplace transform of capital F is Laplace transform of capital F is 1 divided by e to the power, 1 divided by 1 minus e to the power st, integration from 0 to t, e to the power minus st ft dt. So this is what we have obtained. So this is the Laplace transform of a function which is periodic with period capital T. Okay, so let us look at this example. Find the Laplace transform of the function of the periodic function f of t given by this expression. Okay, so this is a piecewise function, piecewise continuous function. That is, when t lies between 0 and 1, the value is 1. And when t lies between 0 and 1 and 2, the value is 0. Okay, so I have drawn the graph here. So for value of t from 0 to 1, it is 1. And then suddenly at t equal to 1, it jumps to 0. And then for values of t from 1 to 2, from 1 to 2, it is 0. And f of t plus 2 is equal to f of t. This expression means the given function is a periodic function with period 2. So that means at t equal to 2, the function will repeat itself. So at t for every interval of length 2, the function will repeat itself. So this will continue and like this and so on. Okay, so this is a periodic function with period 2. And this is the definition of the function inside one period from 0 to 2. Okay, so let us take the Laplace transform of this function. So Laplace transform of f of t, this is by definition, we have seen the property here. We have seen the property. So Laplace transform of f of t is 1 by 1 minus e to the power minus st, s times the period. Here the period is 2, so it becomes 1 minus e to the power minus twice s. Then integral from 0 to capital T, and here capital T is 2. From this expression, we know capital T is 2. So this integral becomes 0 to 2 e to the power minus st f of t dt. Okay. Now let us simplify this. This range of integration 0 to 2. Here the function is defined in two different ranges, 0 to 1, 1 to 2. So when we take the integral, we should split this integral into two integrals. First from 0 to 1, then the other from 1 to 2. Okay, so we should split this integral into two integrals. That is, we should write this integral as the sum of two integrals, where in the first integral, the limit is from 0 to 1. In the second integral, the limit is from 1 to 2. Okay, and we know that in the second interval that is from 1 to 2, the function is 0. Okay, so that means in the second interval 1 to 2, the contribution is 0. Since the function is 0, integration, the definite integration of 0 is 0. Okay, that is why I have kept only the first integral, that is from 0 to 1. So let me write it here to avoid any confusion. Let me write it here. This integral, let me look at this integral only. So this integral should be divided into two integrals, 0 to 1 and integral 1 to 2. Okay, in the interval 0 to 1, the value of the function is 1. Okay, so in the interval 0 to 1, the value of the function is 1. In the interval 1 to 2, the value of the function is 0. So integration of 0, okay, integration of 0 is always 0. So this will not contribute. The definite integration of 0 is 0. So this will not contribute. So the only integral that remains is this integral. And that is what we have obtained here. And we are multiplying by 1 here and multiplication by 1. We simply need not write 1 here. So it's simply e to the power minus st dt. Multiplication by 1, we need not write that multiplication by 1 because the function remains as it is. So this becomes e to the power minus st dt. This coefficient remains unchanged. So the coefficient remains unchanged. So this integral, it becomes e to the power minus st divided by minus s, and the limit from 0 to 1. Okay, let me clear all drawings. So this integral becomes 1 by minus s e to the power minus st from 0 to 1. So this s, we keep it here. So 1 by s times 1 minus e to the power minus twice s. And when we insert the limit, when we put e equal to, because of this minus sign, we put the limit 0 first. So e to the power 0 is 1. Then when we put t equal to 1, we get e to the power minus s. So e to the power minus s. So I get 1 minus e to the power minus s. And here I have 1 minus e to the power minus twice s. So this can be written as e to the power minus s squared, whole square. Okay, e to the power minus twice s, it can be written as, let me write it here, e to the power minus twice s, it can be written as e to the power minus s squared. Okay. So this e to the power minus twice s, it can be written as e to the power minus s squared. That means this is 1 minus e to the power minus s squared. This is 1 minus e to the power minus s. So this is a square minus b square. Okay, a square minus b square के form ले लेगा. So this can be written as a plus b whole into a minus b. Okay, and then a minus b will cancel out with this. A minus b it will cancel out with this, and what remains is only a plus b. So 1 by s times 1 plus e to the power minus s. A square minus b square form the labor. A minus b neighbor. So this is a plus b whole into a minus b. This is a minus b, and a minus b will get cancelled out. This remains e to the power, 1 by s, 1 plus e to the power minus s. Okay, this is fine. Then we have one limiting theorem here. Limiting theorem, this is called initial value theorem. And what does it say? Suppose that the function f of t is continuous on the interval 0 to infinity and is of exponential order alpha, and f prime, that is the derivative of f with respect to t, this is piecewise continuous on the interval 0 to infinity and is of exponential order. And let the Laplace transform of capital F be small f. Then this limit of f of t when t tends to 0 from the right, this is simply equal to limit s tends to infinity s times the Laplace transform of f, where s is a real number. Okay, this is fine. And how do we prove this? The proof is very simple. we already know the Laplace transform of derivative of functions. So the Laplace transform of derivative of function is s times the Laplace transform of the function minus the value of the function at 0. And here, this is the limit. Here we can see that the function is continuous from 0 to infinity. So we take the right hand limit. Okay, right hand limit f0 plus, because the function here is continuous from 0 to infinity. We don't know about the negative side. Okay, so we take the right hand limit, and now we take the limit s tends to infinity. This Laplace transform, we already know the Laplace transform in the limit s tends to infinity is 0 from theorem 2, which we discussed earlier. From theorem 2, this term is 0 when s tends to infinity. So we get 0 on the left hand side. Then this becomes limit s tends to infinity sfs minus f of 0 plus. So that means f of 0 plus is equal to limit s tends to infinity sfs. Okay, so this expression. Let me pause recording